You are in the meeting now.
Recording in progress.
1, 2, 3, 4, 5. Yeah. Okay, cool. So the echo session is being recorded, yeah, right? Because the panel is saying that the session is not being recorded. So, yeah. Okay.
Also
Alright,
Zoom. Can
thanks.
you talk about Zoom also? Yeah. Zoom
Zoom,
connection? Yeah.
yeah, it will be connected via Zoom as well, right? So,
I can't see. Yeah, then Zoom is there. Yeah. Should be all right.
yeah. Okay, Zoom is connected.
Yeah.
Okay, cool.
Zoom is there.
Yep. Yep, that's all good.
Can't log on. Still saying not recorded.
Yeah, she is fixing it.
Yeah.
Okay, so it's all good. Okay, that's all. Alright, thanks. Bye. Yeah, so it won't say over here, but it's definitely recording on the back end. There's some problem with it syncing to say it over here, but it's definitely being recorded on the back end. Just
All
check.
right. All right. Okay.
And the Zoom is connected as well.
Zoom, I can see that. Yeah. So, okay. Thanks. Oh, took some time to fix. Yeah. There you go. Let's start. All right. Move this a little bit far. Week 6, yeah? All right. Should be all right. Here we go. Okay, so what we have been doing from week 5 before the break is we're doing lateral earth pressure theories. We finished almost all, right? Only thing is retaining wall design is left for this week. So there are some problems, tutorial problems we will be doing on Wednesday. We'll try to do one today, okay, over here. Again, most of the geotech is all about problem solving, yeah, just doing some mathematical calculations than theory. So just the summary now, yeah, I'll go again to there was a table, I believe. Where did I put that one in? It should be somewhere. Oh, can't recall. Lateral pressure theories. Yeah, that one, yeah? All right. If I see here, can I project this? Clear, no one in Zoom, so it should be. All right, so now theories, you need to decide which theory to use, right? Either Rankin's theory and a Coulomb's theory. Graphical nowadays is gone. The reason is there used to be time when no computers, no calculators, usually graph and then solve the mathematics. But now it's so powerful computers and the calculators. No need to do the graphical solution anymore, right? So Coulomb's theory, who can tell me? What's the difference, major difference between these two theories? What's the difference? Rankine theory assumes that wall is smooth. Okay, no friction between swirl and then retaining wall. Yeah, Coulomb's theory it considers the friction between wall and swirl. That's it. If the friction is given, choose the Coulomb's theory. If not, easy. Rankine's is easier. Again, there can be different cases. C5 swirl, right? Swirl that has both cohesion and friction. Second one is the clay. We usually do what? It's a cohesion-less swirl, which is sand, right? Yeah, only phi value, not C value. All right. So we call it effective stress analysis. Saturated clay, when there is no friction angle, but there is only cohesion. Good. Those cases depend upon what's this.
Hi, sir.
Yeah.
Hello, sir. Can you share the screen?
I have. Can't you see that?
I can only see you, not the screen, sir.
Oh my God. Now, I need to call to someone or what? Is it conference? Come on. Can I just press something and when you see, just tell me, all right? Yeah?
Okay, sir.
You can now, yeah?
No, not yet. Still not yet.
Who you see now? Your friends here, yeah?
Yeah, I can see my friends here, but not the screen.
Yeah, now you can see me, yeah?
Yeah, I can see you, sir.
How about that? Now.
No, still no, sir.
Oh, come on, now I can't fix this. How they fix that? Because that's the only option I have here, right? Yeah, video conference, and then maybe go back to there. Can you see something different now or no?
No, I just see you, sir.
Then it does not change anything from that computer. They had some problem with the connections and they tried to fix it and they say still not.
Maybe you can Zoom share the. Maybe you can Zoom share the lecture slides.
Yeah, that's what I wanted. But the problem is these zoom icons comes here and then I can't see. You see, this is the projector. I'll try that. Is okay? Yeah. Let's see.
Okay.
Yeah, I'll try, but the problem is, right? When I zoom here, what happens is we can see a lot of zoom icons here in the room. So they block so many things, right? So let's try anyway. Zoom.
Okay, sir.
Yeah, I'll try and see if it does not disturb that much. I can share anyway. Oh, I need to sign in. Here you go. SSO. Hopefully it's all right. Open. Yeah, so that's the meetings. This is to that one, right? Yeah, so we start. Yeah. So now, the computer.
Recording in progress.
I can see your book.
I need to meet you. What's going on? Is it muted everywhere now? Even myself? No, I can't hear you because I have muted you, right? Because it's so annoying. Yeah. Can you unmute, please? Yeah. Now, is it okay now? Can you talk? Oh, this type of thing. I'm focused on teaching, not this.
Yes. Okay, now, sir. I can see the screen.
Okay, so because of these multiple connections, yeah, could you please keep quiet? Otherwise, it's very disturbing. Unless you have something to ask. Is that right? Okay. Where is my mouse now? Disappeared. No, it's not moving when I move.
Yeah, moving.
Moving, but yeah, impossible to go to the place.
Lagging.
Lagging a lot. All right, okay. This is just confirm you can see now, right? Yeah? All right, here you go. But this is
Sir, another day, can you unmute yourself? You are muted on the Zoom.
Did you understand what?
He says that can you mute the Zoom?
But this is muted, right?
I think you are on mute, sir. You cannot hear you.
But if I open that, it will be terribly.
Yeah.
Oh, come on, yeah. I muted myself from the, but I think it should be recorded from there. But the problem is can't display there. I need to call them again. Yeah. Okay, so I'll call them. This is not my thing. Yeah. It's just I need to go out from here first. Sorry, guys. Yeah. Look at this. My mouse does not move. It moves, but like 1994. Yeah. I want to cancel Zoom now. Yeah, this is just getting too annoying. Meeting controls there. Yeah, it's not opening. This is not fun. Close all windows. Come on. Yeah. Go them. Go out. It is not even showing up now.
So that is quite yeah. Up, yeah, a little bit out. Yeah.
But it is not quitting. Did you see up there?
Sir, you can use the task manager control. I think all plus.
Nah, it doesn't
All
work.
plus delete, sir?
Yeah, I know, but now computer is hang. Not moving anything.
Just restart sir once. Yeah.
That is from here. It does not work anyway. So just keep pressing. Yeah.
Yeah.
Why it happens only for me? Look at this. It's not turning off too. Usually 10 seconds, yeah? Okay, look at this. Five 2020 and 2025. Five 2020. Hello, Nat. I have some problem with my room presentation. Yes, ENEC20003. Because it does not. I can't see my computer on the screen monitor. Yeah. I can see myself in both monitors, yeah. And then the presentation is different, yeah. In the touch panel, where is window? Yeah, okay. So window P, yeah. Eh. Window and P, right? And then I can't see anything. It is not showing anything. No. All right. I just called before also, and somebody came and tried to run, and then now frozen and all gone. Ah. Yeah, sure.
You are in the meeting now.
Recording in progress.
Hi, Carly. This is Net. I'm here with your student now. I can see your computer.
So
I just
can
unmute your
you,
presenter mic, okay?
so can you just make sure, because the display says your session is not being recorded. Make sure it is there, recorded.
Yes, okay. Let me fix it for you. 1 minute.
Because it says it's not recording or something.
Okay, 1 minute. Let me. Is this recording? The Zoom is.
Zoom, I can see recording, right?
Yeah,
But
yeah.
the,
1 minute. Let me try to fix it. Yeah.
all right.
Um,
Which one? 5, 6, yeah. That one.
Is this recording on here? I see in echo being is it recording. Let me
Yeah, but
see.
just the display is not showing.
Yeah. Okay. No. Yeah. Yeah. 1 minute.
So can you confirm you can see my?
Yeah. I can see everything. I also got back up.
I can see it now, sir.
Okay, thank you. Yeah.
You keep teaching and I'll fix it for you.
All right. Okay. So keep going to the where I was. Just the theories, right? I was talking. Yeah, isn't it? Okay. Here you go. All right. Okay. So just if there is no friction, just use the Rankin's theory. If there is a friction, use the Coulomb's theory. Of course, you are not supposed to remember those Ka, Kp equations and the things, right? Yeah. So, but just use that particular case. So different types of swirls, we use different technology. Or I wouldn't say different because it's a C0 anyway in one and phi 0 in another. And then sometimes there is a backfill, it's just horizontal. Sometimes backfill is inclined, right? So it's going a lot. And then sometimes there is a surcharge, you have overload. Okay, best of luck for engineers, right? Even if you have a backfill returning well and you overload it, okay, then there is a chance of failure, more failure. And location of water table, yeah, water table will have effect only in gamma. Okay, so that means that, but there is a pressure also, water pressure giving the submerged weight and the water pressure. Water is always perpendicular to the surface it is applied, right? That's what we learned from fluid mechanics anyway. And then wall face, sometimes vertical wall face, sometimes there is a frictionless, sometimes sloping. Look at this, how complicated it will be. There will be a friction, it's a wall is sloping, there is a sloping surcharge, and then backfill and the surcharge. Oh, come on, there are a lot complicated cases. So we cover those all, right? Yeah, and then just use the particular case. Be careful choosing the case because that will have the different analysis. So we did this problem. So now we already know, we did a lot of tutorials also. So now we are going for the retaining wall design. Okay, that's the one, okay? I'm not sure how much we can cover now, but look at here. First thing in retaining wall design is you need to calculate the earth pressure. That's what we did already. Okay, so now we need to, how we calculate earth pressure and the forces is, look at this. If this is a wall, so you need to consider this as a like a wall. Okay, always the lateral earth pressure you calculate in the vertical line over here. All right, up to this level. That's where the lateral earth pressure acts on that. All right, and also there will be usually this passive force is neglected because they are the safe force, right? Yeah. So because to be safe side, they usually neglect the passive force. Okay, only the active force they cover. And also always calculate this point. This is we call toe of the wall, right? Yeah. Some weight will give this type of moment, right? And if any lateral earth pressure gives the other type of moment. Did you see that? One is trying to overturn the wall, another is trying to resist the wall from overturning. Got it? Yeah? So you calculate all forces, that side, resisting as well as overturning forces. And then moments, and then you calculate. There are three things will happen in the wall. One is because the horizontal force here is so strong, this wall moves. Simply that direction. Yeah? Slides. We also call translation. Just moving. Good. Another is force is here. Force gives the moment at this point. So this moment is bigger than the resisting moment giving from the weight of the swell and the wall. So that means what? Then it overturns, right? We call it also rotation. Okay. Third thing is because of this, there is a pressure distribution at the bottom, right? Yeah. Foundation pressure, it gives the wall and everything gives the foundation pressure there. So there is a there may be a failure in foundation soil. What we call this? That's a base pressure bearing capacity failure. I'm not going to cover those bearing capacity theories again, right? We did that week 1 and 2. So we have this basic equation, Hansen, Terzaghi, a lot, right? So we need to first, what we need to do is how much pressure is giving from the wall? Maximum pressure. That should be smaller than what the swell can support, bearing capacity. We'll be doing all tutorials, okay, on Wednesday. One full example, then we know that. It's okay now, right? Yeah, can we go a little bit, again, theory. Look at this. If this is the case, backfill is what? Sloping, all right? Wall is also sloping back, yeah, back face. And then this gives some weight, right? The wall will give this weight. For this point where we are calculating, what happens? This will provide the resisting moment. Okay, it will push that side, right? And then when this, what? The horizontal part of the earth pressure, so that will overturn the wall, trying to overturn the wall. That's resisting, okay? So those type of things, and always calculate based on the toe of the wall, right? That's what the reference point is to calculate all moments. Because that's when it turns, right? Yeah, overturns. Theory, maybe don't know, but we'll do problems, right? Yeah. Sliding, again the same concept. You calculate the total resisting, right? So T is the what? Resisting, sliding resistance. What happens here? How? This is the wall, right? Oh, this is very interesting because it's going down now, right? That's more safer. So some friction there between wall and the swell. So it gives some resistance from sliding. Good, right? Usually we use what? Mu tan theta thing we learn in frictions, right? And then this will push that way. So ratio of these two is the factor of safety against sliding. Good, makes sense? Same thing happens there. So now that's we usually try to get what? More than 1.5 from sliding. We need to be safe, right? Anyway. Also interesting thing is over here, if we neglect the passive, that is giving also the resisting force, that means we are more safer. All right, okay. I will not do this formula thing, right? I'll use the graph and then sketch to calculate those all. So this is sliding, and that is from another textbook, right? So this is the same formula anyway, factor of safety against sliding, right? Another is, we call it rotation overturning. You calculate the moment and then check the moment, right? Yeah, which is overturning moment more or the what? Resisting moment more. Of course, resisting moment should be more, right? By some factor. So that's what the factor of safety overturning is. This is the resisting moment, sum of all divided by overturning moment. You check that. So factor of safety for what they recommend for overturning. Overturning is around 1 or 2.
1.5.
Is it? 1.5 for sliding, I can see. Yeah, well, we can see the different cores and different things. Yeah, that's fine. Okay. So now, third, we need to calculate the bearing pressure. Did you see that here? When the earth pressure presses that way, this side would be more pressure giving to the foundations than the other side. Sometimes it can go like this. What that mean? Already there is a crack, right? There's tension at that side of the base. So there are equations to calculate what is maximum pressure, what is minimum pressure. So this maximum pressure should be what? Below the bearing capacity of soil itself. Is all right? Now, 3, stability check. I think we did that before too, yeah, in our undergraduate. So we'll go a little bit detail in the theory of Rankine's and Coulomb's theory, and I will design the wall. Is okay? So 3 safety check we need to do. Let's do one problem, yeah? Problem is better. I think there is one problem now. Yeah, let's do this. It's a cantilever wall. Yeah, let's do it, eh? Okay, look at here. Oh, maybe geometry, right? So gamma of concrete, did you see that? So can you tell me, based on our discussion, where we need to calculate the pressures? Over here, right? Vertical wall there, right? Can I just draw the line up there? Oh, come on, look at here, my drawing. All right, here you go. That's the The pressure must be calculated from that point to that point. All right, yeah? So there will be what? Pressure given by what? This is surcharge there. So that means what? It will give the constant, right? Yeah? Like this pressure. I'm drawing the pressure diagram, right? This something, it comes by itself, right? That's the pressure diagram. What is this size? Who can tell me? How wide is this?
1.8?
No, I'm talking about the pressure diagram. I did that, right? Not the distance at the moment. So this would be Ka, right? Yeah, Ka multiplied by Q. Q, Ka. Active earth pressure coefficient multiplied by the discharge, right? Yeah, the surcharge, sorry, not the discharge. Surcharge there. So this would be, we need to calculate Ka. Is the friction given in here or not? Wall friction. Yes, right? We represent delta as a wall friction, right? Yeah? So that means what theory we need to use? Coulomb's theory. Can you calculate Ka from the Coulomb's theory now? Come on, yeah, Ka value for this. I'll open up the equation and you calculate, all right? Yeah, there you go. Ka there. All right? So Ka must be, we need to calculate that first. So it's a Coulomb's theory, inclined backfill, right? Active pressure. Can we go back and copy the equation?
Yeah.
What is the Coulomb's theory? This is Coulomb, right? Yeah. So where is the active pressure? This is passive and active. Yeah, we need to calculate Ka using this equation, right? Because earth pressure coefficient, right? So alpha, I need to check what is alpha. Alpha is at the bottom. I think in our problem, that is 90 degree. Good. Can you write that now? Alpha equal 90 degree on the piece of paper there. And another one is what we need is phi, is I think just in our problem, how much is the phi? We will check that, right? Just write phi and I'll leave it for now. So alpha, we already know. Delta is the friction angle. We also have that in our problem. What we need? Beta. What is beta here? Beta is slope of the backfill. That's also we know, right? Yeah? Just copy this equation first. Can you copy in your paper? So Ka, I'll just write here and I'll show you, right? The tutorials and the example. Yeah? Ka equal to sine square alpha plus phi, sine square alpha plus phi divided by, so sine square alpha, sine square alpha, sine alpha minus delta, sine alpha minus delta, and then that's the 1 plus square root sine phi plus delta, sine phi plus delta is sine phi minus beta, sine phi minus beta, okay, divided by sine alpha minus delta, sine alpha minus delta, and sine alpha plus beta. Sine alpha plus beta. Hopefully I typed the correct one, right? Alpha, beta, sine alpha minus delta there, phi minus beta, phi plus delta, alpha minus delta there. Okay, that's all right. Okay, so I got this equation. Let's all of it can calculate for our case, right? This is for the backfill. So beta is 8 degree, beta equal to 8, right? And then phi, friction angle is 25. Phi equal to 25. Okay, delta equal to friction angle, which is 15. Delta equal to 15. And what else we need here? Alpha equal to 90 degree. The reason why alpha 90 is what? Vertical wall, right? There, when the backfill meets the wall is vertical. That's it. All right. How much you got? Can you put that in and then calculate? Sine square 90 plus 25 divided by sine square 90, sine 90 minus 15, and then square root of 1 plus, is that what the formula is? Yeah, 1 plus square root is, so that one is what, sine alpha is 25 plus 15. Okay, sine phi is 25 minus beta is 8, I think, yeah? Divided by sine 90, take away 15, and the sine 90 plus beta is 8. Should be all right. Beta is 8. Okay, I'll just go back and have a quick look on the formula now, whether I copied all right or not. Oh, all of it is square again. Did you see 1 plus the bottom part is square? I'm talking about here, right? That's all square again. There. All right, so I need to do this close and square. Come on, yeah. Get that one. Ka first, right? Yeah. How much you got? Ka. Yeah. Well, did they have one table? Just come and check from the table if they have that. Otherwise, we need to compute this wall. No, there is no table. All right. How much? Based on what I have here, it's 0.41.
0.78, sir.
78? Anybody else got the same thing?
So can you share your document once?
Sure. Just the same formula I put in. So 90 sine square 90 plus 25, sine square 90, sine 90 take away 15,
19 minus 15.
and a 1 plus sine 40 there. That's a sine 17. That's a sine 75 and a sine 98.
But we get like 0.78.
How much?
I don't know what.
Yeah, same, 0.78.
Oh, then we did the formula wrong somewhere. Did you get exactly this one? Sine squared 90 plus 25, yeah? So can I rewrite again that
Just a minute, sir.
sine square, what is it? It's 15, right? 115? 115 divided by sine square 90 is 1. Okay.
So, above is square, yeah? 0.71, but we got it.
So sine that is 75, yeah? So now that's a, and then square root 1 plus, there is a 1 plus, oh, there is a square root there.
Is this square root outside the square root?
No, after 1 plus square root, yeah.
Oh,
Yeah, I remember now the formula, there was a square root, I forgot to put in, yeah? Yeah, there is a square root, did you see that, there, down there?
After 1 plus, yeah?
Yeah, after 1 plus is square root, I think you get that.
Just
Square root, and then with 1, it's a square. Okay.
square 0.408.
408, okay, that is closer. Okay, anyway, we get that using the equation when we have time. All right, so let's not waste just the competition. All right, don't waste time to do this, right? Yeah, but we need to confirm. So can I write that? What is 0.408, right? Good, 408. So now what happens is, because it's giving, we haven't calculated that. How much will be this height from this point to that point? because this is 8-degree angle, yeah? And the horizontal distance from there to there is, how much is it? 3 meters. How much will be that now? So 3 vertical is sine, right? So 3 sine 8. Can you do that now? 3 sine 8.
0.41.
0.41, yeah, okay. So just write 0.41. Then you get the total height. Can you compute and put the total height? 0.41 plus 6.1 plus 0.9, yeah? All the wall, right? We need that facing. Okay. So 41, yeah? How much is that? They calculated 42 here.
It is 10, we use 10 here, sir, 10.
Huh?
10. Not sine.
No, this is vertical we are calculating, right? Oh, this is, yeah, okay. Because this is the base is known, right? Okay, come on.
142.
Look at this now. Here you go. That's the one. This part is 3, yeah? Look at my writing. Yay, I can't write, sorry guys. Maybe I'll show here. It's easy for me. All right, okay. So now, I think we calculated that. We need to do, this is 3. Okay, that's how much is that we need to find.
0.4.
And then we know this is 3, this is 8-degree, right? So if it is x, so tan 8 equal x over 3, right? Yeah? So what? Opposite over adjacent, right? So x equal to 3 tan 8, sorry, not sine. Because base was given, not the hypotenuse, right? So, okay. Well, here you go. 0.42, yeah?
Yeah.
Good, right? So I can put in my diagram now. So 0.42 there. So how much is total now? Thank you. 42 plus 6.8, 6.1 plus 0.9. How much is that total? Total height. 0.42 plus 6.1 plus 0.9.
7.42?
7.42. Okay, that's all right. Let's write there. So that's why I know how much the height of this pressure diagram is. Good. So now, can you calculate how much it will be now, that part? Oh, the pressure also, it goes to what? Goes to in angle, right? When you move that by 8-degree, so it will be what? Cos 8, right? Horizontal is cos, isn't it? Yeah? So now, pressure is, you need to do this cos 8-degree also here. Do you understand why I did this?
I can't do it.
You can't get it?
Yeah.
All right, here you go. So can I show you here? All right, the reason is, this is the pressure here, right?
Yes.
Not horizontal. If pressure was horizontal, it will be just QKA. But we need to move that pressure to the horizontal, right? From hypotenuse to adjacent,
Okay.
right? Yeah, that's from that to that. Okay, so that means we need to do cos 8, right? Just to move the pressure from that to horizontal.
Horizontal component.
Yeah, correct. Yeah. Good. Yeah. So let's go back to here. So now, can you compute how much is that now? This width of this?
QKA.
Q is what? 20. Ka is 0.408 and cos 8. Yeah. Oh, that's the one I will need to. That may be, and then multiply by 7.42 to get the total, right? So we'll do that a little bit later. So 8 points. They didn't calculate it this way, so 8.08, right? Yeah, 0.08. All right. That's the horizontal pressure that's giving. So we need to convert this. So total, how much is the area now? Can you just calculate this area now, total force? Area of this pressure diagram. I want to check something there. How much is the area now? 8.08 multiplied by 7.42.
59.95.
58, yeah, very close. That's fine. Okay, that's good. So that will be, total area is that. No. So where it will be acting, because there is a friction there, remember?
Yeah.
So it is not horizontal because it will with the angle of the friction. So in this case, it will be this way, one horizontal, and then there is an angle, the force is acting in the angle. Angle is, what is the friction angle there? 20, 15, yeah?
15 degree.
15. You see now that one, 15 degree. Oh, that will be very small to neglect that cosette also. There will be hardly any change if you do without cosette. Cosette value is how? How much is that? It's a big one, yeah?
0.99. Nearly 1.
Yeah, nearly 1 means it doesn't change that much, isn't it? Yeah, that makes sense. Good. So there will be two parts, right? Vertical force and then horizontal force of that. So this one we calculated 50, what you said? 59 something?
59.9.
They have calculated
59.95.
Oh, okay, 59.95, right? Can I write that now? So can you convert this now into horizontal and vertical?
Yeah.
Horizontal you do cos 15 degree,
Yeah.
and then vertical you do sin 15, all right?
57.90.
90. So they have here is 58 point something. Yeah, that's fine. Okay, 50. Can I write just 58 for now?
Yeah.
Just make sure, but we need to compute there, all right? So how much will be vertical now?
Vertical. Sine. It's like
15.5152.
Okay, 15.52. What they have here is about 15.7. Oh, come on, that's the same thing, right? Yeah, 15.8, right? Yeah? Look at this. So we calculated just by surcharge until now.
Yeah.
And so we know the locations, right? Locations would be somewhere there at that angle. So we know the horizontal component. We know the vertical component now. Vertical component X in this line. Did you see that? Yeah, that's the line vertical. Horizontal is what? It's a rectangle, so it's a halfway through. Above the base, isn't it? Right? Halfway through. Now, another one. Can we compute for the swell, due to swell, not surcharge? Come on. Can I just remove that now? Yeah, just draw another pressure diagram by swell. So that means it will be triangle, right? Yeah. At the beginning will be no overburden things, but at the bottom it will be huge. How much will be this now? Ka gamma d. You remember we did that last time, all right? So gamma d. That's it. Can you calculate now? Depth. How much it would be? 0.408 multiplied by gamma saturated, right? That's the swell. So 18 times, and the D, depth is how much we have? 7.42. How much is the bottom one? Give me this value, please. Yeah. 0.408 multiplied by 18 times 7.42. How much you got?
54.5.
How much?
54.1.
54.1? 49, right? 54.49, yeah? All right. So now can you calculate the area for the force now? Yeah? You need to calculate area of a triangle, easy, yeah? So total force. So it acts as the same angle now, right? But it will be 1/3 from the bottom. All right, so that's the force is acting. How much is force now? I love doing the geometrical way here, right? So that's how you calculate area instead of remembering the force formula. Yeah, draw the pressure diagram and then how much you got? Area of this triangle? Half times that times 7.42.
202.17.
202.17. So they got 203 here. The reason is they use 0.41 as Ka. All right, there will be slightly different. It does not matter that much. Yeah, so it's a 0.4202. Yeah.
Yeah.
Can I write just 202? Okay, for now. That's all right. Now again, it will have vertical component as well as it will have horizontal component. How much will be horizontal? This angle will be friction angle. How much was that? 15. All right, that's it. So how much is horizontal?
195.28.
Yeah, so 196 they got. So that's fine, right? 196, and then vertical one around 50 something.
Yeah, 52.6.
52. All right. Did you see that now? So 52. I want to clarify a little bit because I can't write there. I want a little bit open up there and then do here, right? Look at here. What happens is because of the surcharge, okay? So this is what the pressure diagram is, right? Yeah? And then angle is again because of the friction, otherwise it will be horizontal. All right, if there was no friction between wall and the backfill, it would be horizontal. So that's why two components there. Same thing for the backfill material overburden. So it goes that, and again it comes in the angle, but one will be horizontal, one will be vertical. You got it? So why we need to separate horizontal and vertical? Because one is trying to overturn the wall, another is trying to resist the wall. Yeah, you see, from overturning. That's it. That's good. So this is, we know, that's we know. Can you tell me now just roughly how much is that one? Is 16? Yeah, no, this is 58 or 59? Yeah. That one is about 16. Yeah, just right. Very simple one. Yeah. Vertical one, that one is 53?
Yeah, 53.
52, 53 around because of the just the decimal places. So it will be 190,
95.
196. All right. So that's what we got. So that's because of what? Just because of the pressure from the side. Now is straightforward because we need to consider there will be other things. What will be? Can I go to my there? Now we need to divide. So this is the one area. It gives resisting. That's the area it pulls down, isn't it? Somewhere there. How about this block? That's also provides some resistance, right? Yeah, this block. So we also need to calculate, oh, look at my drawing, but that's the second area. Good? Yeah? How about the third area? This is the area at the bottom, right? Yeah? So that's less, right? This is 1, okay? Because of this backfill within the wall, it's a 2, and this bottom is 3. All right, yeah. Look at this. Even they slope this side. Okay, for me, that's a terrible design. Why not they made vertical, right? But again, if we make a slope, there will be two cases, right? Yeah. One is at the same height as a rectangle. Yeah, and there is like a triangle here, a small triangle, right? This is because of the slope. You see, this all. If you ignore this, I think they have said somewhere ignore or something, right? So passive resistance, then we need to calculate now weight of 3, weight of 4, weight of 5, right? So can you calculate now how much will be the weight of this triangle edge at the top of backfill? Half base. Now weight I'm calculating, right? There's the total, that's a force, okay? So W, let's say W1 equal to half. What is base? How far is that base? 3?
Yeah.
How much is height? We just calculated before, 0.42. And then that's the area we calculated. We need to multiply by what? Unit weight of soil there. Yeah, to get the going down. So you multiply by, how much is that? So unit weight at that time, they didn't give different, right? So it should be 18. All right, can you compute that? First, what is the first ways? How much is the force going down? We use the unit, okay? Lengthwise is the 1, right? So that's why we don't need to go with the lengthwise. It's just the cross section. How much you got? 11.3. Okay, that's what we have. This is a kilonewton going down. Good. So now, how about the 2? What is the weight of 2? W2? So this will be very easy, right? Rectangle. 3 times what? 3 times 6.1? 6.1?
Yeah.
Height is 6.1, right? That 2 part, isn't it? Yeah? Multiply by gamma. Gamma is unit weight is 18 again. Yeah? Can you compute that for me, please?
329.
329. That's what they have here. Newton, right? Okay. Number 3, W3. What I assume is the 3. 3 is base, right? Yeah?
Yeah.
Hopefully they assume the same, or if not, then we will compare that one. Or 3 the vertical, doesn't matter. So can we do the 3 now? How much weight pulling down 3? What's the area of that? It's a concrete, yeah? Oh, look at this, I overrode it. I don't know, is it 23.5? Is that correct? The unit weight?
Yeah, so 23.5.
Yeah, 23.5. Okay, that's the 3, all right? Okay, that's what we said. W3 equal to area, what? How long is that? 4.8?
Yeah.
4.8 times height is
0.9.
0.9 and multiply by density of concrete,
It's 2.
23.5. Yeah, give me that one.
101.52.
How much you got this?
63.45.
63? 3 meters. 0.9, right? Yeah, the calculator is slightly different. I think they misinterpreted this 1. They use 1 in the multiplying, but 0.9 is the thickness, right? Yeah, R is all right. So how much is that? You said
101.5.
101.5. Yeah, that's it. They have all right. Good. So now how about 4? How much is the 4? How much is the height? 6.1, right? Yeah. W4. I will not do this too because 1 in 20 is very small, right? That area, the triangle is very small, right? Yeah. I would really, because that gives not the what they call overturning force, it will resist the force, yeah. So that should be more safer, isn't it, to ignore that, yeah. So for now, just ignore what they have done here in the calculations. You can check. How much is the 4? So 0.4 times. 0.4 times what's the height?
6.1.
6.1 times what's the density of concrete? Same, yeah? 23.5, yeah? Can you give me that one?
7.34.
7.34. So maybe it will be very small other part, but I don't know how much it will be. We can compute because 1 in 20, right? Yeah?
Yes.
So how much it would be? Can I just 1 in 20 there? So let's write that W5 then. All right? Why not? W5. So it's a 1 in 20. So that part would be how much? Okay, can I draw here? I'll draw here, all right? See. So that was like this, right? Yeah? That was a little bit slope like that, yeah? So height is 6.1, right? Yeah? If it was 1, it was 20, yeah? 1 in 20 means that, isn't it? So if it is 6.1, how much will be there? If it was 1, it is 20, right? 6.1, it should be very small. How much is that?
0.3.
0.3, right? That part is 0.3. All right? So now calculate the area, how much it will come. I want to check, right? Yeah? Half base is what? 0.3?
Yeah.
Right? Times height is 6.1, isn't it?
Yeah.
So, and multiply by concrete, so 23.5. If it comes a lot, then I'll add that, okay? Okay. How much is that? It does, maybe it is coming a little bit, yeah.
It's 21.5.
Yeah, 21.5. They calculated around 25, that's fine. Okay, so 21.5. You understand what I mean, yeah? So that's how the ways there is a small batter, so they want to use that too. But 21 maybe, yeah, that is a big weight, kilonewton, yeah. All right, we did all weight, right? There is nothing left. Anything left? Yeah, we need to check, right? We did the base, we did that, and we did that, 2 of them. It's good? All right, we finish. So these all are all vertical forces. Remember, always pulling down only. There is no horizontal component of that. You remember here, we did these 2 horizontal and vertical component from the pressure, but these are just giving the vertical pressure only. Done. Now let's check for. How about sliding? How much total vertical force? Can we combine them all?
Yeah.
Because you see always the friction is vertical force and the friction angle between wall and the swell. Okay, we need to 10 phi, right? That's what we do to calculate friction. So can I calculate now? How much is the total vertical? Sum of B. Sum of B, come on, let's do. So can I move this here? So sum of B, what we got is, here you go, right? Sum of V, all of them. I'm talking about all vertical forces. But again, for moment, they act in different location. So that's why we need to calculate moment differently. But just the total force for now, sliding. How much is the first force? 11.3 plus 329 plus 101.5 plus 57 plus 0.34. Let's add those also, 21.5. And then vertical component of 2 pressures.
Yeah.
What was that? 16 and 53, yeah?
53.
Can you check that now? How much is total vertical forces now acting there? I think we didn't miss any, right? So all those weights and then as well as pressure. Yeah, that's it.
329. It's okay. 11.3.
Total vertical, everything vertical. 600 something they have calculated here. I want to see.
Oh, we've got just less than 600.
Is it?
Yes.
I think we missed something then. what was missing? All vertical forces they calculated is
21.5, that's okay.
so 11.3, that's correct. 3, oh, this is not 92. I think I wrote wrong. 29. Yeah? Even it will be less than, yeah, 329, 101.5, so 57, yeah, that's fine. They said 21, 57.16 and 53, which is around, yeah, it should be more than 600, based on what they have calculated here. Can you do again? So this 400 already there, right? And so 500, oh, yeah, this is 53 at the end. Yeah, it will be more than 600. Come on. How much? 11.3 plus 329 plus 101.5 plus 57.534 plus 21.5, 1653. How much you got?
589.64. Yeah. I've got 590.
How much? 590?
Yeah.
Why they have this then? They have all vertical force, they have 650. Anything missing there? When I check here, nothing is missing, right? 11.3, that's we have, yeah? 329, we do have that. And then 57, that's there. And then 21, 25 around that, yeah, 21 there. And then 60, we miss 60. What is 60 there?
It's the surcharge, sir. But it didn't include the surcharge.
It's a surcharge, but we added surcharge already. 6 is surcharge. Oh, surcharge weight itself also, right? Not on the pressure giving by the surcharge, but there is a surcharge. We miss that, yeah? Direct weight, yeah? Two things, right? Okay, thanks for reminding. Direct weight giving from the surcharge, as well as the pressure from the surcharge due to SWOT. So we need to weight the surcharge too. All right, 3 times what? 20? But we cannot do 320. We need to do this cos 8-degree thing, right? If you want to really translate to horizontal. But it will hardly make any difference, 0.9 something, right? It will be very close. Okay, they ignore that. Okay, 600, how much that now? 600, around 50, yeah? Now is all good. This is from surcharge. I missed that. Yeah. Okay. So now we've done all, right? So now what we need to sliding. How much will be sliding now? So total. So mu, right? 10 phi. Can I check the formula now? Sliding. I just need to do sliding force. Yeah. What is that? This one, yeah? Oh, you see, you need to use from that to that, what is phi shears angle, and then factor of safety. This is the what we did a lot, right? Yeah, all of them. So we need to do this total vertical force and the 10 phi V. Can we write that? How much is the resisting now? So that's resisting is what? The mu, right? Resisting to slide, right? So it would be, what would they say is, now that's the total vertical force 650 times 10 angle. What's the phi? We need to use what? Half CS to that. What they have used here. I want to just use that and then slide in. Yeah. So 25. So they didn't modify anything because 1/3 to 2/3 they say, but they wrote the 25-degree angle. That's same as that. I think that should be given at the bottom, right, problem? There may be given exactly that value. At the base, yeah, and they gave, right? So you just use the base of the angle, 25-degree. Is okay? So how much you got? How much is that? Resisting sliding. 1025 is what? 1045 is around 1. It must be less than 1, right? Yeah, but way less, 1 over root 3. How much is it?
Exactly.
300? 650 times 1025 degree.
$303.09.
So yeah, they have 305, so this must be all right, okay? 09, okay, 303 kilonewton. So now you see, this is what this side is pulling, 303 kilonewton. And that's a pushing. Well, how much was the total horizontal force pushing? Oh, we haven't calculated that, right? Yeah? So total is 196 there, I can see there, and a 59. Only two, yeah?
Yeah.
Because all other giving the vertical one, right? So this is not the horizontal. So that's it. So at the top, how much it will be?
225.
196 point. No, not point now. Plus 59. Yeah. How much is that?
225.
225.
255. 255.
255. Right. Okay. So now you see, is resisting that much, pulling out that much. If we don't consider factor of safety, it looks safe. Yeah. Because resisting is, how much is resisting? 303, and the pushing out is what? 255. So let's do factor of safety. So 303 divided by 255. Can you do that? How much is the factor of safety now? 1.2, yeah?
Yeah.
Around, yeah, they have calculated 1.2 anyway. All right? Oh, is it enough? More than 1.5 is, yeah, that's what they prefer. But again, these points we are saying 1.5, 1.2, they are just arbitrary now. You need to use the local code. They do have in local council, country, you need to have this factor of safety. We need to achieve that. But over here, just the book says, some book says 1.5, some 1.2, some 1.8. Don't believe on those exact numbers, right? So you need to have a local code, the retaining wall design code, when you work in the council, and satisfy those factor of safety requirements. Okay? For now, we can say it's not sliding, but very critical, right? If, let's say 0.99, we can immediately, okay, no, it's not safe. Yeah, but 1.2, think about that. So sliding done, right? How about overturning? What time is it?
We need to calculate moment.
Overturning. Now we need to calculate moment. Okay, so now we will do one problem, right? Yeah, overturning. Overturning is there are 6 weights, right? W1, W2, W3, W4, W5, and then also there is a surcharge coming, yeah? And then there are also what? 2, because of the surcharge pressure as well as earth pressure is coming, right? They have also horizontal and vertical components. So vertical component will resist, right? And then horizontal component will overturn. How much the overturning moment? We can do that now. Come on. MO, sum of all MO. 196 is the horizontal component from the swell, right? Yeah? You can see there. Can I show? Yeah, 196 you can see, yeah? That's good. 196, where it is acting? What distance from the toe of the wall? From the bottom here.
Middle of the wall, sir.
So what corner of the wall, right? So how high it is?
Middle of the.
Not middle. Which one? 196 is a triangle. Triangle is 1/3.
S by 3.
Yeah, S by 3. So what is S? 7.1.
7.1.
7.42, I think.
Yeah.
7.4.
2 by 3. Yeah, that's what the first part, right?
2.47.
So that's it. Plus, we have another one also because of the surcharge, right? 59 also pushing. Yeah, 59. What is the distance for this force? Half, right? Midway through. Yeah, 7.42 divided by 2. Okay, can you calculate what is the overturning moment? That moment that causes the wall to overturn this way. It shouldn't be that big. How much they have? I'll check and verify. Yeah, come on.
$703.
Yeah, 701 they calculated. That's all right. Okay.
3.66.
Kilonewton, right? So how about the coming? This is what it, I'll write like this, right, to understand. That's how this moment is acting, right, trying to overturn the wall. Good? Yeah? So how many words is going that? Resisting moment now? Yeah, so that's that from the toe, right? There are so many of them, right? Let's start with these two components first, okay?
Yeah.
So what is the vertical component of 53, right? Yeah? How far is that point? 53 times how far is that point from the toe? So all distance, right, is the face of the wall. Can I go to my lecture and then count? So over here is a vertical acting, right? How far from this here? You need to find this corner. So total is 4.8. Make sense?
Yeah.
Distance of vertical acting, 4.8. Plus the other one, because of the surcharge also, can I come back now? Yeah, I'm talking about this 16 now.
Yeah.
That's also the same. Yeah, because it always acts in the face of the wall, right? Pressure from the soil is always face of the wall. That's it. So that's a 2 I calculated. Now all those weights we calculated before. Plus, what is W1? How much was total in the first 11.3? Where it works, where it acts. Can I go back now to show you, right? Where it works is over here, right? Vertical 1/3 there. Do you understand? Over there, weight is the center of gravity for the triangle is 1/3 from the base. Good, over here. So now, how much is distance? Total distance is 4.8 minus 1/3 of how long from here to here? Oh, not that one. Then. Let's take that from here to here. 3 meter, right? 1/3 of 3 meter is 1 less. So 3.8. Make sense? How I did is total I calculated, right? That is a 3, right? And then 1.8, right? Total distance is 4.8, but minus 1/3 of 3. So just 1 minus, so it should be 3.8. All right. Then the second one. Second one is this. This one, where it acts in the center is a rectangle. In the center, how much is acting? How much was the for W2? 329?
Yeah, 329.
Multiply by, what is the distance of that force?
3/2 plus
1.8 plus 3/2.
Yeah.
How much is that?
3.3.
3.3. All right. Good. We did the second one. Good. And then third is, we assume third is the base, yeah? The bottom one, isn't it? Yeah. So bottom, what did, how much was the W3? 101.5 total force. And where is the location of that? It's the center of 4.8. How much is that? 2.4. You understand what I'm doing, yeah?
Yeah.
Just trying to find the location of that force from the toe of the wall. That's it. All right, yeah. So now another one is number 4. Number 4 was 57.34, 57.34. Yeah, 57.34. So where it acts, right? Multiply by, that is the center there. Oh, okay. So now 1.8 minus 0.2. Yeah, that's it, right? 1.8 minus, yeah, good. So 1.6. Yeah, that's easy. So now triangle that part, okay? Oh, come on, that's, I wanted to ignore already. So that's a very small part. So it will be, how much is 1.8, take away 0.4, take away 0.3, I think we calculated, right, best? So it should be 0.1 take away. Can I do that now? That was 21 something. 21.5 multiply by 1.8 is total, right? Take away 1. Oh, I'm not showing you this, right? Yeah, 1.8 minus 0.4 at the top, minus little bit of, so 0.2. Can you calculate that, how much it would be? And then, oh, we haven't used the pressure because of the surcharge. We also forgot before. So now we need to do the top part. When it acts, this surcharge 20 times area. We need to calculate area, right? How long is that one is, oh, maybe just use 3 meters, right? 60, we use the kilonewton force. Where it acts is the center. Okay, so 60 times, can you do that now? 60 times. Center is, where is that? 1.8 plus 3/2. Is it 3.3?
Yeah.
We did that before, yeah?
Yeah.
All right, 3.3. Good. Anything we missed? No, right? Okay, can you do the calculate resisting moment, all of them? Total together, please, guys. I want to open this for you to see. All right, can you sum them all? I think 1, 2, they are because of the pressures. 1, 2, 3, 4, 5, 6. I think that's it. How much is that? They have calculated overturning moment is around 1300. Okay, let's see. Resisting moment, right? Oh, why I wrote MO? Guys, yeah, you need to tell me they are resisting, right? That's going that way, not that way, all right? MR. How much you got? 53, that, multiply that, blah, 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 so many. Please press calculator. Too much? Not too much. It depends on how complicated wall is, right? How many parts we need to break it down. Otherwise, if it's a simple wall, it shouldn't take that much time.
Solution is available on the presentation.
Yeah, of course I have. And also, we will do tutorial again on Wednesday, right? And those are also available anyway. You can verify your thing, but just learn now the concept, right? How is resisting, overturning, those type of things. That's it. Come on. How much you got? No?
1496.
1496. All right. You got a little bit more than what they have here, but it's okay. But for now, just to write, yeah. What they got here. It's maybe distance, anything. Oh, come on, check. Oh, don't know. Resisting, right? Yeah? Overturning moment. 703. Oh, they didn't separate it that like that. But anyway, so what is the factor of safety now for overturning? So 1496 divided by 703, how much is that? Because always resisting divided by overturning, yeah? Yeah, almost 2, yeah?
2.12.
Oh, that's good. 2 is okay, yeah? Double safety anyway. All right, okay. Guys, yeah, so listen, I have here, right? You can check. So there is a one safety check left. What is that? Foundation pressure.
Yeah.
So for that, we need to calculate eccentricity, where those loads are applied, right? And then how far is from base of the footing to that application of the load, vertical, horizontal, total together. And then that's the eccentricity. That gives us one side pressure is small, another side pressure more. Okay, so maximum pressure we get there, and that maximum pressure we compare with the swell bearing capacity. All right, we'll do one whole problem again, right, on Wednesday, and maybe 2, who knows, right? Let's see, and then we'll final those type of things. Is okay? I need to, because sorry, we missed a lot of it at the beginning because of these issues. I think solutions are here, we can just see, okay? But they can compute differently, but the concept is again, right? What are resisting, what are overturning, and what are sliding, what is resisting to slide. We need to check those, and should be all right. So what they say at the end, or 2 point something, yeah, okay. So that's 3.8, so there's a factor of safety. Oh, they computed in different way, rotation, but that's okay. So I think we have the book, right? And that's what we are using, and that's all right. Formula we are using is this now, right? Yeah, resisting over overturning total moment, yeah. That will be easier. And then wall is not that much safe, looks like. Look at this, 0.39. Bearing capacity is not satisfactory. We haven't done that, yeah? Based on these calculations, bearing capacity is not satisfactory, what they say. But you can check these calculations. And there are tutorial problems we'll be doing on Wednesday, all of them, right? Maybe 2 problems, hopefully we'll do both, but at least 1 in full, so you know that. Any questions for me? Yeah, now just take a little bit lunch and come here to teach me. All right, yeah? So the student connecting from Zoom in your team time, please share, right? Not one person presenting. So just take the rotation. At the beginning, start by one, and then give to another, and then finish by other, right? Yeah? And then also I would ask you guys to ask questions to your friends' presentations.
Yeah.
You can ask your own team also, okay? I'll leave it free, but maybe that is, you are not going to ask, or at least you need to ask for others, right? Asking questions, right? Let's do it in the afternoon and 1 o'clock. Is okay? Okay, thank you. That's it.